Hi, welcome to a little problem-solving tutorial using Newton's second law and kinematics. I hope you will enjoy our time together. Pause the video and take your time to read the problem. Then work through as much as you can. If you get stuck, continue the video to get some help to proceed, and then pause again. Working through the problem yourself first is still number one approach to learning. You may make mistake along the way, but that is what I am here for. I will be your physics guide. The first step in the solving strategy is to make a sketch. I made two sketches. The reason is that these problems are often disguised in various forms in standard textbook problems. There is no difference whether it is a person or motor pulling it up the incline plane. The next step is determine forces acting on the box through a free body diagram. In this case, we have forces of pull, gravity, normal, and friction. Remember, the normal force is perpendicular to the contact surface. Now that we have our forces, we establish a reference frame, which allows us to decompose the vectors into components suitable for solving Newton's second law in component form. We are free to choose such reference frame, but we can make life easier for us with a smart choice. How do we make a smart choice? Through practice. By choosing the shown frame, we only have one vector that requires trigonometry to decompose. Okay, now we decompose the vectors into their x and y components. In this step, I prefer to also utilize the known force equations for forces of gravity and friction. If you struggle with figuring out the angle to use in finding the components using trigonometry, I have added a little sketch here. Imagine we overlay a standard-oriented x and y frame on top. Then we rotate it to coincide with our chosen frame. The angle rotated is the same as the inclined angle. Then it will be more obvious where the angle theta is. It is the angle between the force of gravity and the negative y-axis. Finally, we can insert the force components into Newton's second law in component form, that is, in its x and y components. We now have two equations but three unknowns, the normal force and the two acceleration components. This is not in our favor. Fear not, my darlings, the equation of constraint is our savior as it often will be. The y-coordinate for the box is 0 and will remain 0 as the box is constrained to move along the incline. That implies that the change in y position is 0 and the y acceleration must also be 0. Let us then repeat step 6. Awesome, we have two equations and two unknowns. We are rocking this problem. Using our favorite method, we can solve this. At the end of the video, I have listed the symbolic Python scripts I used to solve it. For the remaining parts, we will use kinematics and the definition of work for motion in one dimension. We should recognize that the acceleration is constant, enabling us to employ the equations of kinematics that are derived under the assumption of constant acceleration.